All right, our viewers. After some time, I'm back. This is Mr. Hyper, and this time I've come with a lesson about pure mathematics. And here we are going to look at a topic of integration. The topic is integration, and I'm going to start with integration of trigonometric functions that have got even powers. Then after that, I'll also talk about odd powers. From there, we shall progress with other sections. So I'm saying that we are going to begin with integration of trigonometric functions with even powers. Before I start, members, I would love we share this link and we subscribe, so that we hope everyone outside there that is very much interested. Now, at the moment you see the word even powers, what should come into your mind is that we are going to totally be applying double angle formula, double angle formula. As the name suggests, trigonometric functions, it implies that we need some idea of trigonometry. And to remind you something small, let's remind ourselves from our trigonometry. We normally say that if we have cosine of angles alpha plus alpha, the fact that I'm talking about double angle, it means that if my angle is alpha, its double is going to be 2 alpha, which is alpha plus alpha. I want you to really remember that the expansion of the cosine, when we are adding cos 2 alpha, this one, it seems as if it is cos 2 alpha, but let's expand. It is going to be cos alpha, cos alpha, cos alpha, cos alpha, minus sine alpha, sine alpha. And now, when you work on this, it is going to be cos 2 alpha is equals to cos squared of alpha minus sine squared alpha. Looking at this, if I call this one my equation 1, this is the first double angle formula in terms of cos that I can put on table. Then 2, we also, here, you can really see that either from this, we have that either, you can see that either cos 2 alpha is going to be equal to cos squared alpha. We can leave everything in terms of cos minus. We have got some other identity in trigonometry, which is very common. I think this is the parent identity, sine squared alpha plus cos squared alpha is equals to 1, meaning that by all means I can express sine squared alpha in terms of cos, and it's going to be sine squared alpha is 1 minus cos squared alpha. Now, when we substitute this one here, it is going to be 1 minus cos squared alpha. This one will give me my cos twice alpha is going to be equal to cos squared alpha minus 1 plus cos squared alpha, implying that when you work on this, cos squared alpha plus cos squared alpha, that is 2 cos squared alpha, then minus 1. I call this one my equation 2. Then another one, we can also bring it out as cos 2 alpha. Now we can also express this cos squared alpha in terms of sine, meaning that here cos squared alpha can also be equal to 1 minus sine squared alpha. Very interesting. Now, when you look at this, you can have it as 1 minus sine squared alpha minus another sine squared alpha. Very interesting, implying that our cos 2 alpha is equals to 1 minus 2 sine squared alpha. This is my equation 3. Now, I really need to know, or I really need to see what if I express this one. What if I make cos squared alpha the subject? And here, what if I make sine squared alpha the subject before we look at the real application? So here you can see that from equation 2, we can make cos squared alpha the subject, so that our cos 2 alpha plus 1 is equals to 2 cos squared alpha, then implying that our cos squared alpha is going to be a half of cos 2 alpha plus a 1. Similarly, from equation 3, we shall see that our sine squared alpha is going to be equal to our sine squared alpha is going to be equaling to 1 minus cos 2 alpha, and everything we shall divide it by 2, making it a half of 1 minus cos 2 alpha. Now, I'm going to apply these ones here. I'm going to apply cos squared alpha and sine squared alpha in integrating the even trigonometric function. So what we need is to quote this formula here, and we also need to quote this formula here. Now, let's look at examples, and then we see how best we can maneuver. Before also, since I've decided to remind you, let me also remind you more. Reminder again, before we start these integrals, I want to remind you that for trigonometric functions, we derive the integrals from the derivatives. We remember that from differentiation, if we differentiate sine of x, we strictly get cos x. All right, implying that when we integrate cos x dx, this one will always give us sine x plus a constant. What does it imply? When you differentiate sine, you get cos. So when you integrate cos, you should get sine. 2, I want you to know that when you differentiate a cos x, you get negative sine x. What about when you integrate sine? When you integrate sine x dx, you should be able to get negative cos x. All right, plus a constant of integration. 3, I want you to know that when you differentiate tan x, you get sec squared x, implying that when you integrate a sec square x, when you integrate a sec square x dx, automatically you'll be able to get your tan x plus a constant. Another one, if we differentiate sec x, we get sec x tan x. We get sec x tan x, implying that when you integrate sec x tan x, we shall strictly, of course, dx, we shall strictly be getting sec x plus a constant of integration. Another one, when we differentiate a cosec or a cosecant or a cosec, when we differentiate cosec x, we get negative cosec x cot x, negative cos x cot x, implying that when we integrate that cosec x cot x dx, should be able to get negative cosec x plus a constant. Another one, when we differentiate cot, when we differentiate a cot, we get negative cosec squared x, implying that when we integrate cosec squared x, dx, we strictly get negative cot x plus a constant. These ones we shall reach time, maybe I do use some proofs and we see how we can see. Then another thing which I wanted to remind you, when we differentiate like sine 2x, we drop the magnitude of the angle, which is 2, and it becomes cos 2x, implying that when we integrate that cos 2x dx, for this case, we don't drop the magnitude. Instead, we divide by 2, so it will be a half sine 2x plus a constant of integration, etc. So let's look at the application of this. Let's look at the application of this. Let's do some examples and we see. Examples number 1. I will do what we can, then maybe I'll give you some exercise numbers to try. A, find Roman 1, two, three, four, five, then B, evaluate, sine power 6 of x, then dx, then C, find Roman 1, tan power 4x dx, Roman 2, Roman 3, so I want us to go through some of these integrals. Okay, we're going to work on these integrals. Then I will do some, then I will leave you with others for your own consumption as you try also. It will be a longer video, but I will try to condense. Let me begin with the first one. We are told to integrate cos power 4, cos squared x dx. Now, we already know what cos squared x is from the double angle formulas. So allow me to say that cos squared x dx is the same as the integral of a half into 1 plus cos of 2x. That is what we derived. All right. Meaning that this is the same as the integral of a half plus I'm multiplying a half inside, so a half also cos 2x everything dx. When you integrate a half, you get a half x. So we shall get a half x plus here we shall drop a power. We shall drop it down, so it will be a quarter sine 2x plus a constant of integration. As simple as that. You are going to review. Let me do you another example and then we see. Integral of course power 4 x dx. Now, the moment you have this power 4, there is no way how you can rush it as a double. You must first make it a square so that you carry it out as a double angle. All right, so what are we going to do? What are we going to do? What you're going to do, we are going to say that cos power 4x dx is the same as cos squared x, then everything squared dx. All right. So that I can easily substitute cos squared x because I already know it from the double angle. So it is going to be integral of a half. All right. This is a half. The whole of this, a half, then 1 plus cos 2x, everything squared then dx, meaning that this square affects this half also. So it is the same as integral of a quarter, then into 1 plus cos 2x, everything squared, then dx. The simple thing to do here is to expand this bracket. It is 1 plus cos 2x times another 1 plus cos 2x, so that we have it as an integral of a quarter into 1 plus 2 cos 2x after expansion, then plus cos squared 2x dx. You can really see that this one is the same as the integral of a quarter, all right, plus when you multiply a quarter, it is going to be a half cos 2x, of course, plus now this one is another double angle. So what do? We shall say plus a quarter. Remember, this a quarter is multiplying enjoy everything. So plus a quarter, the integral of cos squared 2x dx. So that when you expand, when you integrate here, actually we shall integrate this separate. So it is going to be a quarter x plus this 2 will come down, so it will be a quarter sine 2x, then plus a quarter integral of, now this one is cos squared, but 2x, so its double angle would be 4x. Its double angle would be 4x. So it is going to be a half into 1 plus cos 4x this time, not 2x, because the double angle of 2x is 4x, then dx. So that the overall thing is a quarter x plus a quarter sine 2x then plus 1 over 8. We integrate it, it will be 1 over 8x. Plus this 8, f4 will come down, so it will be 1 over 32 sine 4x plus a constant of integration. A quarter plus 1 over 8 is going to be 3 over 8x plus a quarter sine of 2x, then plus 1 over 32 sine 4x plus a constant of integration. Very, very interesting. Let me do you another question on those questions which I've given you. And that question is, let me give you some logical one. Integral cos power 4 5x dx. If you have this is the same as the integral first square cos square, but 5x, but everything will be squared again dx. So this is the same as when you look at this is going to be a half. All right, it is going to be a half 1 plus cos 10x. All right, then squared, because the double angle 5x is 10, and therefore my aspect holds. What does it imply? X multiply, it is going to become a quarter. All right, it's going to become a quarter, and I can move it outside. All right, I can move it outside, a quarter. Then into 1 plus, I can expand this to cos 10x, then plus cos squared 10x dx, of course. So this is going to be a quarter x plus 2 over 10 sine 10x. All right. Then plus a quarter integral of cos squared 10x dx. Here, you can work on it separately so that your answer becomes a quarter x plus 2 over 10 sine 10x, then plus, now the integral of this is going to be a quarter. Still, we are going to move out a half, so times a half, then integral, we shall remain with 1 plus cos 20x, because it is a double angle of 10 already, then dx. So this is going to give you a quarter x plus 1 over 20. So this is 40 under 2, we reduced 1 over 20. So 1 over 20 sine 10x plus, this is 1 over 8 here, so it will be 1 over 8x when you multiply the integral of 1, which is x, then plus 1 over, this is the 20 will go down, 20 times 8, that is 1 over 60, 1 over 160, sine 20 x plus a constant c. when you bring this one and this one together, it's going to be 3 over 8x plus 1 over 20 sine 10x plus 1 over 160 sine 20x plus a constant of integration. From there, you're going to allow me to integrate some other number. I want you to keep replaying this video so that maybe you understand better. And in case of any comments, you let me know. Let us integrate zero, a quarter pi, sine power of 6x dx. Wow. Don't fear anything here. This is the easiest. So it is the integral from 0, a quarter pi of sine squared x, then to the power 3 dx. By laws of indices, when the 3 and the 2 multiply, they become 6, as you can see it. But this is going to be equal to, since everything we keep in terms of x, let me work without the limits. I'll bring the limits at the end. So it is going to be integral sine squared x power 3 dx, of course, is going to be equal to integral a half 1 minus cos 2x. Now for sine, it is 1 minus cos 2x, the angles we derived. Then, of course, to the power 3 dx. When you cube this, we're going to have our thing as the integral. Take time, expand, so it will be 1 minus 3 cos 2x. Cubing plus 3 cos squared x. One can use Pascal's triangle. Expand this, then of course minus cos cubed 2x dx. All right. This is the same as remember, after expanding this a half, it becomes 1 over 8. So I have 1 over 8 here. So it is going to be 1 over 8. I first work on this. So into x, it's going to be into x minus 3 out of 2 sine 2x plus this 1 over 8 also multiplies here, so it is going to be 1 over 8, but even I can move out a 3, so it becomes 3 out of 80 integral of cos squared, cos squared 2x, cos squared 2x, all right, dx, minus 1 over 8 times that, it will be minus 1 over 8 integral cos cubed 2x dx. Wow. When you expand this, or when you work on this, it is going to be 1 over 8x minus 3 out of 16 sine 2x plus 3 over 8 times a half, because I have to convert this to a half to double angles. A half, then integral cos squared is going to become 1 plus cos, but this one will become a double angle, it will be 4x dx, then minus 1 over 8 integral. You know, this is the same as cos squared x times cos squared 2x times cos 2x. So it is going to be 1 minus sine squared 2x, then times cos 2x dx. Allow me move like this up. And this is going to be equal to 1 over 8x minus 3 over 16 sine 2x plus 3 over 16. I'm here. Then we integrate here, you'll have x. So it will be into x plus a quarter sine 4x. Why? We integrate cos 4x, you get a quarter sine 4x. Then minus 1 over 8. When you look at this one here, well, we can expand. It is going to be cos 2x. Of course, integral minus sine squared 2x cos 2x dx. Now, this is the same as 1 over 8x minus 3 over 16 sine 2x plus, when you multiply here, 3 over 16x, we multiply it here, plus 3, this is 64. It will be 3 over 64. Sine 4x minus, when you integrate this one here, a half will come, so it will be 1 over 16. All right, sine 2x. Here, when we integrate this, it is going to be 1 over 8 cos times a half and a third of sine cube 2x. And if I bring in the limits now from 0 to a quarter pi, expanding this, 1 over 8x, 3 over 16, we're going to get 5 over 16x minus a quarter sine 2x, because you have 3 over 16 sine 2x, 1 over 16 sine 2x, 3 over 64, sine 2x. So this is going to be minus a quarter sine 2x plus 3 over 64 sine 4x, then plus 1 over 48, 1648 sine cubed 2x from 0 to a quarter pi. So this is going to be 5 over 64 pi. You try entering the pi. So when you put your x, we are substituting x as pi. Okay, so minus a quarter, substitute appropriately, plus 1/48. So this one will give us, to reduce to 1/192, the LCM, is it? Then we shall have 15 pi minus 44. Do direct substitutions and you get the answer. Final, I'm going to do the final, then I let you people try and see what will happen. I want you to try and see what can happen. I want to do the integral of cot power 4x dx. When we look at a cot, this is the same as cot squared x times another cot squared x. But we know that a cot squared x, I can maintain 1. But I know from trigonometry that cot squared x plus 1 is a cosec square x. That is from our simple trig. All right, so that one we can apply it. We know that these ones are also paramount. You need to know them. Cos squared x plus sine squared x is equals to 1. We also know that 1 plus tan squared x is equals to sec squared x. We also know that 1 plus cot squared x is equals to cosec squared x. So what does it mean? I can easily substitute for my cot as cosec minus 1. So it is cosec squared x minus 1, everything dx. Now here, you can expand the bracket so that it becomes cot squared x cosec squared x. All right. Of course, then minus cot squared x, everything dx. Now, you can simplify this as cot squared x cosec square x, because this one we can at least work on it separate, then minus the integral also of cot square x dx. We realized that here from the summary I made for you at the start, we said that when you have a cosec cot being integrated, all right, we get you are integrating cot square. So here one can relate cot. All right, one can easily relate a cot. Okay, let me give you a hint here. Hint, because it may be too hectic for us. If I let you to be cot x, it means that du, when you differentiate a cot, you get negative cosec squared du. No, cos squared x, but then dx. Meaning that my dx is going to be equaling to negative du out of cosec squared x. So that I work on this one only first. So the integral of cot squared x cosec squared x dx is the same as the integral. This is u, but here u was cot x, meaning cot squared x is u squared. cosec of course squared x dx. Now instead of dx, I'll substitute with the du out of cosec squared x, of course with a negative outside. Cosec square will go with the cosec square, and here we'll be having the integral, negative integral of u squared du, which is negative u cubed out of 3 plus c, but u is a cot, so it will be negative cot cubed x out of 3. So that all of this one becomes negative a third cot cubed of x. Very interesting. Then when you integrate cot square, we can also briefly rate. Of course, you know that if we cot square is the same as cot square is the same as cos square x sine square x dx. But cos square x the same as 1 minus sine square x over everything sine square x integral. This is the same as cos dx. This is the same as 1 minus sine square x. We start dividing 1 over this minus this over this. So it is going to be 1 over sine square x, which is cosec square x, then minus sine squared over sine squared, that is 1 dx everything. Now, when you integrate cosec square from the summary I gave you, we get negative cot x. So that here we shall have minus negative cot x. Then when you integrate 1, you get x. All right, so our final answer is going to be negative a third cot cubed x plus cot x plus x plus a constant of integration. Very interesting. So thank you for viewing. I'm going to send to record a video about integration of odd powers. After that, I will go to integration that involves the application of sine and tan substitutions. Thank you for watching us. Stay blessed.